Hello, Math Study students, and welcome to your online lesson. Today we'll be continuing where we left off on arithmetic sequences, and we'll be talking about something known as an arithmetic series, or the sum of an arithmetic sequence. We're going to use a formula to find that sum of any arithmetic series, and we'll know we're successful when we can correctly identify a series as arithmetic, create a formula for that series, and use that formula to calculate the sum of the series. An arithmetic series is the sum of consecutive terms of an arithmetic sequence. So by sum, we mean adding together. So previously, we had looked at sequences that were just lists of numbers like 4, 10, 16, 22, so on and so forth. And we knew that they each had a common difference, which is to subtract backwards. I could see the difference between each of these is 6 as I subtract backwards. And we could find missing terms using a general formula or a general term or an nth term. But now what we want to do is say we take that exact same sequence and we now make it a list of numbers being added together. Suddenly this has become a series where we're adding numbers up. And so that's really the main difference between a series and a sequence. Now, oftentimes on IB level questions, they won't even use the word series. They will simply just say, find the sum of the sequence, or the sum of the sequence up to a certain value. And in order to do that, rather than just having to add up a bunch of numbers in our calculator, we have a couple formulas. And you'll notice here it uses the S of n, S sub n. So again, S and a subscript, meaning a low script like a submarine, so S sub n, where n is our term number, just like before when we had U sub n, but the S is referring to the sum. So this would be the sum of the first n terms. Sum of the first n terms. So if n was 7, I would be adding up or doing the sum of those first 7 terms, the first term, second, third, fourth, fifth, sixth, and 7th. All right, there's 2 formulas that we have to achieve this. They're both in our formula packet. The formula packet, we'll write them as a big run-on, but you have to pick one or the other. Now, the first formula we've got here has a u sub 1 and a u sub n. Well, n is not just any term. It is the term that we're adding up to. So again, if we had s sub, let's say 7 here, that would mean I'm adding up the first 7 terms. And I would be using that same 7 here and that same 7 here, which indicates that this, u sub 1, is still my first term, but this here would be my last term that I'm adding up, or the 7th term in the case that I was just talking about. But what we need to know is our first term, and we need to know our last term that we're adding up. And that's really it. If we know those things, and again, know the value of the number or the term that we want to add up to, we can plug that in for both of these ends. But again, you're plugging in an actual number here for u sub 1, our first term, and then you're plugging in an actual value for u sub n, which again is whichever term you want to add up to, the 7th term, the 80th term. And you're not just putting that value of n in, you're putting the actual term number. Now, all of that is well and good, and this formula looks relatively easy, but this is not the formula you will use most times. You just won't have that last term. So instead, we have this hybrid formula that borrows some things from our previous formula, u sub n, or u sub 1 plus n minus 1 times d, and it combines it with this other formula that we have above. So for this, all we need to have is our common difference and our first term, and then we still need to know our n value, the number of terms that we're adding up to. So let's try out some of these formulas on some examples and explore series just a little bit more. So here I've got a series. It has 7 terms in it. And the first thing we want to do is find the sum of the series by simply adding. So that's what we would probably do if we didn't know anything else or have these formulas. So we can do 2 plus 5, which gives me 7, plus 8 gives me 15, plus another 11 gets me up to 26, plus another 14 gets me up to 40, plus 17 gets me up to 57, and then another 20 gets me up to 77. So that is my answer. And you say, well, that wasn't so hard. Mr. Peacock just did that in his head, or we could do it on our calculator. But that was only for 7 numbers. What if it was 700 numbers? And let's say they weren't all listed out for me. I wouldn't want to have to go through all those steps. So what we're going to do here is we're going to look at the 2 different formulas, try using it, and if we can do it for a simple example like this, then we know we can apply that to a much more complicated one. So I will start here with this first formula, and again, this is the one we don't use very often, but we can use it here, and the reason we can use it here is because we know the first term, it's 2, and we know the term that we're going to add up to, which is the last term in the sequence, or series in this case, which is 20. So I have 7 terms that I want to add up, so I'm going to put S sub 7 is equal to, and again, there's 7 terms that are adding up, and I'm going to divide that by 2. And now in parentheses, I'm putting in, once again, the first term that I have here, which was 2, plus the last term I have, which is 20. And now I need to throw this into a calculator. A couple things to keep in mind. There is a group here, so when you're putting this in the calculator, I would recommend using parentheses. And if you want to simplify beforehand, you certainly can do that. So we have S sub 7 is equal to 3.5, or that's what 7 divided by 2 is. 7 halves is 3.5 times 22. All right, and I will throw this into the calculator, and we end up with 77. So this notation is saying the sum of the first 7 terms is equal to 77. All right, we're going to try it again now with our last formula. And even though this formula is a little bigger, it's the one that we want to be comfortable using because it's the one we will most often have to use. So let me erase this part as well, but we'll keep the 77 up as a reference. So we're using this formula now. Again, we have 7 terms, so our n is going to be 7. So I will have S sub 7 is equal to n over 2. Well, our n is the same thing we had here, which is the number of terms that we're adding up. So 7 terms divided by 2 times 2 times our first term. Well, our first term was still 2. Plus n minus 1. Well, n is the number of terms that we're adding up, which is 7 minus 1. And then our common difference. Well, we didn't figure out the common difference before, but to get our common difference, we subtract backwards. So we would have 5 minus 2, which is equal to 3. But just to make sure it's common, let's check it on the next one. 8 minus 5 also gives me 3. And then 11 minus 8 also gives me 3. So I definitely have a common difference. It is a common difference of 3. I can plug that in. Again, if I throw parentheses around this, I can type this all into my calculator in one single step. But if you want to clean it up a little bit first, you're welcome to do that. So again, 7 divided by 2 is 3.5. 2 times 2 is 4. 7 minus 1, which we have right here, is 6. And 6 times 3 is 18. So we're going to end up with 3.5 times 22, which is the same thing we had before, which gets us down to 77. So again, it was probably easier just to add up these 7 numbers here, but when we're dealing with large lists of numbers all getting added, we want to use one of the formulas for that. All right, moving on to our second example. We have an arithmetic series that has 9 terms. The first term is 3, and the last term is 59. So the first term is 3, last term is 59. So we can actually notate that. We know we have 9 terms, so our n is essentially going to be 9. The first term is 3, so that would be u sub 1 is equal to 3. And the last term is 59. So that would be u sub 9. Now, how did I know that was the 9th term, or u sub 9? Well, because there were 9 terms, and it said the last one is 59. So the 9th term must be 59, u sub 9, the 9th term. Well, this is great because I know the first term and I know the last term, which means I can use the shorter formula, which is S sub n is equal to n over 2 times u sub 1, our first term, plus u sub n, which will be the last term that we're adding up here. So we have the sum of the first 9 terms is equal to 9 divided by 2. We have our u sub 1, our first term, which we know is 3, plus our 9th term, or our last term, which is 59. Continuing on, sum of my first 9 terms is equal to 4.5 times 62. And now I'm going to reach for a calculator and simplify this. And our answer is 279. So that tells us the sum of the first 9 terms is 279. And even though this was 9 terms, this formula was much faster than adding up those 9 terms because I didn't even know what those terms were. They weren't listed out for me. I would have to actually figure them out. And every time I'm figuring out a term, that's a potential for a simple mistake. So I've got all these different places I can make errors. And here there's only a couple things I'm plugging into the formula. Again, the first term and the last term, and then the number of terms. You'll notice also that we had a 9 here, replacing our s sub n, and then we had 9 for the n over 2, and then once again, there is this n value here, which is referring to the 9th term, or the last term, which we knew was 59. All right, we'll do one last example here. So here they list out the first 4 values of the term, or of the series, and we want to find the sum up to the 20th term. So still not too high as far as what we want to use. The question is, do we know the value of the 20th term? We do not. So we don't know the last value of the term, which means we have to use the slightly longer formula. And like I said, that's the one that we'll most commonly use. So let me write that down for us. We have s sub n is equal to n over 2 times 2 u sub 1 plus n minus 1 times d. All right, so what do we need for this formula? Well, we need to know how many terms we're adding up, and that's both of these n's, this n as well. We need to know the value of our first term, that is our u sub 1, and we need to know our common difference, that is our d right here. So I know my first term, I'll circle that in blue. So the 25 I know right away, so I can write 2 times 25. And I still need to know the number of terms that I'm adding up. Well, that I have. That is 20. So that means I'm going to find the sum of my first 20 terms. And that's equal to 20 divided by 2. And it's also my n value. So I have 20 minus 1. And then the only thing I don't have is my common difference, which I had indicated earlier here in green. So to find my common difference, I subtract backwards. And again, don't fall into a trap where you're just like doing it in your head. Literally write it out. 21.5 minus 25 gives me 3.5. Except it's negative because I started off with a smaller value and I was subtracting a larger value. So negative 3.5. And that's going to have a huge impact on how our answer changes when we do this problem. We can check it once again. We take 18 now and subtract the term that was before that, 21.5. And again, we have negative because we're subtracting a bigger number from a smaller number, 3.5. So we can see that is our common difference. So I'm going to put that in at the end of my formula here, negative 3.5, and then close off my parentheses. All right, so now I'm going to plug all this into the calculator. Again, if I want to simplify it a little bit ahead of time, I certainly can. 20 divided by 2 is 10. 2 times 25 is 50. 20 minus 1 would give me 19, but then I'm multiplying that by a negative 3.5. We do need the parentheses all around that negative. So I'm going to plug all this into my calculator in a single step and see what our answer. And I get negative 165. So that would be the sum of the first 20 terms of this series. Now you might be asking, how can this be negative? None of the numbers here are negative. But you'll notice that the numbers are going down. And so in the course of just 4 terms here, we've already lost a value of 10. 10.5 to be exact. And then as we continue on, we'll keep going down and down and down, and we're going to end up with some very low values. And those values are going to get added, so they're going to compound. We don't need to get down to a term as low as negative 165, but we're eventually going to get into negative values. Those will get added, and we'll end up with this large negative sum here. So that was our lesson on arithmetic series, which again is the sum of an arithmetic sequence. We looked at 2 different formulas to allow us to do that. And until next time, that concludes our lesson.